Hello, my name is Sourodeep Deb, and today I'll be talking about the last subsection in section 12.3, which is projectile motion. Okay, before I talk about projectile motion, I would like to talk about something more basic. But I have a pen in my hand over here. What happened? I threw it up, and it came down. This is true for any object on Earth. When you throw it up, it will eventually come downward. This is because on Earth we have a force called gravity. And let's actually write that out. We can denote that as F of g is equal to the mass of an object times gravity. But we're not done. Force, unlike a scalar, has two distinguishing things: a sign and a component, because vectors have direction and scalars do not have a direction. So we'll put a negative sign here and we'll give it a j component. Gravity was actually created by scientist Sir Isaac Newton, and Newton also discovered his second law of motion, which we say is force is equal to mass times acceleration. Why am I telling you this? Because using Newton's second law of motion, we are able to derive what the acceleration of any object on Earth is, and then we can derive the equations of projectile motion. We just derived this as equal to negative mg with the j component, and we can cancel the masses on both sides. So then we get our acceleration is equal to negative g with the j component. G is the gravitational constant, so we can say that g is equal to 32 feet per second squared, or g is equal to 9.8 meters per second squared. So now let's derive the equations of projectile motion. Suppose I have a projectile with some initial conditions. Let's say this projectile has a mass of m. We can say it has an initial velocity v0, some initial position above the ground, which we'll write as r0, and I'm launching it at some angle theta. We know that a is equal to negative g with a j component. So now let's simply derive the velocity of the projectile. V of t is simply the integral of a of t with respect to time. So let's integrate this function, and we get negative g with the j component dt, and this is equal to negative gt j plus initial condition c, right? We just said that the initial condition for velocity is v0 over here. So we can say that c is equal to v0, and then we can write v of t is equal to v0 minus gtj. So for a projectile, this is the velocity. Now let's find the position of a projectile, which is actually what characterizes a projectile as going in projectile motion or not. So we know that r of t is the integral of the velocity function with respect to time. So let's simply integrate this function, and what we get is the integral of v0 minus gt with the j component dt, and this is going to equal to v0 t minus half gt squared j plus initial condition c. And like I said earlier, our initial condition for position is r0. So we can say c is equal to r0 this time, and then we get our characteristic equation as r of t is equal to r0 plus v0 t minus half gt squared. Something very cool to realize over here is that the position function is actually a parabola. So let's draw this out because this parabola tells us a lot of things about projectile motion. So I'll call this my r of t, and I'll call this my t. I'll not draw t less than 0 because simply time cannot be less than 0. Time starts from 0. I'll start with an initial condition, r naught, and this will be some height h above the ground. Because we're working with vectors, and height is above the ground, and this is a vertical distance above the ground, not a horizontal distance, I will simply give it j as a component. Now let's draw a parabola. So this could be the path of a projectile, and let's see over here, we have our v naught launched at some angle theta. Let's bring this over here really quickly so we can see, we can actually decompose this velocity into components because, like we know, velocity is simply not a scalar. It's a vector with components, a direction, and and also a magnitude, which is v naught in this case. So v naught is over here. This is theta. And what we know is that it'll have a horizontal and vertical component. This horizontal component is going to be equal to the magnitude of the velocity vector times cosine theta with the I component because it's moving to the right, or it could be moving to the left, and simply it just has a horizontal component of motion, not any vertical component. For Vy, actually this is Vx, and for Vy, we can simply say that Vy is equal to the magnitude of the velocity vector times sine theta with a j component. Why j component? Because the Vy is going up. It's moving in a vertical direction, not a horizontal direction. So given that we've rewritten r of r naught and v naught, now let's rewrite our position function. So r of t is simply equal to r naught, which is going to be h with a j component, plus we can rewrite this as v naught cosine theta times t with the I component plus v naught sine theta t with the j component minus half gt squared j. And let's finally rewrite this by grouping all the I terms and all the j terms together so we can get a proper r vector. So what we get is our r vector, which is our position vector, will simply be v naught cosine theta t I plus h. Well, now we're grouping all the j terms together. So this will be equal to h plus v naught sine theta j, not j because j will go outside, t minus half gt squared, and we'll give this a j. And this is what we call the standard equation of motion for a projectile. Let's test our understanding by doing a practice problem. So suppose I throw a projectile and the mass is really irrelevant. Let's just say a mass m, right? Why is mass irrelevant? Because we simply don't see mass coming in this equation. I throw it with that initial velocity of v naught equals 100 meters per second. Some initial angle theta is 30 degrees above the ground. And now I want to find some things. First, actually, let's define one more condition. I'll give some initial height above the ground as 1.5 meters. I want to define a couple things now. What is the range of the projectile? And what is the maximum height of the projectile? let's go back to this for a second. Our range is simply this. To find the range, simply, we can find the time it takes over the whole path, and because range is in the horizontal direction, we can multiply that by this. We can multiply by v naught cosine theta. Height max is a little trickier. So this is our r of t, and now let's actually differentiate that to get v of t. So you get v of t is equal to v naught cosine theta I plus v naught sine theta minus gtj. What do we know about this? What this tells us is that the velocity vector, which is basically when the projectile moves along the path, the velocity at every point is the same. Sorry, it's the same in the x direction. Even here, we'll see that this is going to be v naught cosine theta. And even just before we're about to hit the ground, we'll see v naught cosine theta. What we also know is that over here, we're giving it has some initial velocity, not some initial velocity, but it has some velocity, which is v naught sine theta. Over here, this v naught sine theta is equal to 0, and then we'll see that because of gravity, eventually starts going downwards. So over here, we'll have v naught sine theta. So that's that. Something important to realize is that force makes something stop motion or change motion, right? There's no force in the horizontal direction. There's only a force in the vertical direction, which is gravity, like we defined earlier up here, right? So that's why this component changes, but this component remains constant. So let's start by writing our position function as r equals, let's actually plug in some stuff here. V naught cosine theta t, right? So we'll have our v naught cosine theta t I plus h plus v naught sine theta t minus half gt squared j. And this is going to simply be equal to 100 times cosine 30, right? 100 times cosine 30 is simply 100 times root 3 over 2 ti plus 1.5 plus 100 times sine 30, which is going to be equal to half t minus half gt square j. Okay, and simply we can write this out as 50 root 3 I time with a time I plus 1.5 plus 50 t minus half gt squared, the j component. Pretty straightforward. And maximum height, we know that the y component of velocity will be equal to 0. So from this range equation, we get ry of t is equal to, actually let me rewrite this because it's not the range completely. We'll write this in lowercase r, and we'll say this is r. Ry of t is going to be equal to 1.5 plus 50t minus half gt squared j. So we know that the vertical component of velocity will simply be vy of t equals r prime y of t, which is going to be equal to 50 minus gt j. At height max, at the max height, r v of y of t is 0, so we can simply say that 50 minus gt is equal to 0, and then we get t is equal to 50 divided by g, and like I defined earlier, g is going to be 9.8. And if you calculate this out, we simply get 5.102. This is a time to reach it. So now let's plug this back into our Ry of t, and let's see what we get. And this, if we calculate this out, will simply give us our time as, this will give us our position as 129.1 meters. So that will be our max height. Now we want to find the range. The range is when the projectile is at the ground, which is when the y component of the motion of the motion of the position is 0. So let's simply set Ry of t equals 0 to find the total time of the whole flight. So then what do we get? We get 1.5 plus 50 t minus half gt squared is equal to 0. So then what do we get? We get half gt squared minus 50t, by bringing this there, minus 1.5 equals 0. We can solve for t using the quadratic formula, which is going to be t equals 50 plus minus, it's going to be 50 squared minus 4, negative 1.5, g over 2, over, and this is going to be g. So we can simply calculate this out, and we'll get two values actually. We'll get a negative and a positive because of the plus minus. Time can't be negative like I said earlier, so we'll take the positive value, and you can calculate this yourself. You'll get 10.234 seconds. Now with this, we know that range is in the horizontal direction, not the vertical direction. So to find range, we can simply plug in this time into the x component. So what do we know here? We know that Rx of t is going to be equal to 50 root 3 ti. So let's simply plug this in. Rx of 10.234 will be equal to 50 root 3 times 10.234, which is going to give us 886.3 meters. So these are our answers. The max height is 129.1 meters and the range is 86.3 meters. That's all for projectile motion. I hope you enjoyed this video. Yeah, thank you.